Today's speaker, Emma Strubell from the University of Massachusetts at Amherst, where she's doing a PhD in the College of Computer and Information Science?
Yes.
Information and
Sciences.
Computer
CICS. Information and Computer Sciences.
Right.
Yeah, sorry. Very important.
With a focus on natural language processing and machine learning, and in particular looking at deep learning that is sort of hardware aware. She's been applying this in several different directions, including scientific knowledge bases, the Zuckerberg Foundation, and advanced materials synthesis. I don't know, are we going to hear anything about advanced materials synthesis today? Okay, good. All right. She's been an intern at Amazon and at Google. She's had an IBM fellowship. And she's here fresh from her Best Paper Award at the Empirical Methods in Natural Language Processing Conference last summer, which is one of the most competitive conferences in NLP. She also has a Best Paper Award from an ACL conference, too. So with no further ado, Emma, take it away.
Thank you. Thanks, Martha, for the introduction. So today I'm excited to tell you all about my work at the intersection of natural language processing and machine learning, where I work to bridge the gap between state-of-the-art NLP models and real-world practitioners. All right, so as researchers at the cutting edge of scientific discovery, we're all eager to address the many complex and deeply intertwined challenges facing society today, such as how to reduce energy consumption, how to prioritize and accelerate scientific research, how to combat socially ingrained bias on the basis of race, gender, and socioeconomic status. And of course, how can we elect government officials and enact evidence-based policies that reflect our views and scholarship on all these critical issues? So we need to make decisions in these important areas, and we want those decisions to be informed by data. And much of the data that we can use to address these problems can be found in text. But raw text alone doesn't give us these insights. It contains all this rich information, but in order to access that information in a principled way and aggregate over billions of tweets or millions of research articles, we have to process that raw text into a structured form. So, for example, an important application in materials science is developing more environmentally friendly processes and materials for manufacturing, for example, cell phone and computer batteries. So these material synthesis processes that we want to optimize are only found in the free-form text of journal articles. So I have a collaboration with Elsa Olivetti, who's faculty at MIT Materials Science and Engineering, and we're working on automatically extracting these advanced materials synthesis recipes from the text of millions of research articles so that we can aggregate over all these known recipes to both identify the most efficient ones and ultimately to propose new and better recipes from the promising building blocks that we've mined from the text. So in order to do this, we need to do some natural language processing on this text in order to extract structured information that we can actually work with. So first, we need to identify the basic entities participating in the recipe and their types. Then we need to extract the relationships between those entities, both within and across sentences in the article. So this is a very high-level example of how we use NLP to extract structured data from text. And right now is a really exciting time to be doing NLP because many of these basic extraction tasks have come of age. So looking at the common example of syntactic parsing, while 25 years ago, accuracy on this task began around 70, more advanced machine learning techniques have increased accuracy to above 90. And in the last 5 years, thanks to advances in hardware and methodology, neural networks have brought this accuracy to above 95. So this has made NLP no longer just an object of study, but an important technology that major companies are running at scale on the entire web. And so this has emboldened other practitioners to want to have this structure on their data as well, such as my collaborators in materials science. And while we are able to extract some useful information in these new domains, accuracy is not as high on this new data, which contains different jargon and different distributions over underlying structures than the news article benchmarks that our state-of-the-art models are trained on. So we have a lot more work to do to develop machine learning models that have robust performance on the endless new domains where we wish to gain insights from text. So in order to use NLP to gain these insights, we need algorithms that are not only robust, but we also need them to be fast in order to leverage the massive amount of data that's available. So for example, the New York Times alone posts around 250 new news articles a day, and there's almost 500,000 new tweets per minute. So we need machine learning models with efficiency that scales to this amount of data. And this is not only because we care about turnaround time, but also because we care about lowering energy cost, both in terms of money, so that these techniques are actually accessible to not just prominent tech companies, but also to a wide range of practitioners. And also because we care about the cost of the environment, of all the energy that's required to run these models. All right, so in the remainder of my talk, I'm going to present some of my recent work on developing fast and robust models for NLP, and discuss some related directions that I'm excited to pursue in the future. So I'm going to begin by describing linguistically-informed self-attention, which is a neural network model for extracting semantic structure from text that leverages syntax to improve generalization to new domains. And I'm going to start by showing you exactly what I mean when I talk about semantic and syntactic structure. Okay, so here we have a sentence divided into tokens. A typical NLP pipeline works by annotating text with increasingly complex linguistic structure. So the first level of annotations that we typically assign to words is part of speech tags. So this is labeling tokens as nouns, verbs, etc. And next we can assign edges between tokens to form a syntactic parse tree. So this tells us how the words actually relate to each other. And we usually label the edges in the syntax tree. So for example, in this sentence, the subject of the verb awards is committee, and the direct object is Nobel. The first step towards understanding the semantics or meaning of the sentence is identifying the predicates, or words indicating actions, in the sentence. So in this sentence, we'd identify the predicates awards and advanced. So now we want to identify the arguments participating in each of these predicates. And basic models for this can be built by designing rules over the syntax tree, but this doesn't scale well across diverse vocabularies and sentence structures. So instead, what we typically do is directly label the spans corresponding to the predicates and their arguments in the sentence. So this is called semantic role labeling, or SRL. So with respect to the predicate awards, the agent argument, or the one doing the awarding, is committee. Its theme, or the thing being awarded, is the Nobel, and the beneficiary, or the one receiving the award, is Strickland. So this is the semantic role labeling with respect to the predicate awards. And similarly, with respect to the predicate advanced, the agent is Strickland and the theme is optics. So these are the two semantic role labelings of the sentence with respect to the two predicates. And we're specifically using the PropBank SRL framework, which was developed here by Martha, which assigns more general argument labels that are shared across all the predicates in our corpus. So that's what these labels actually look like in practice. So we want to extract semantics, but as you can see, this task is deeply intertwined with syntax. And historically, SRL models have relied heavily on syntax. So looking at the last 10 years of SRL on a popular benchmark for the task, early SRL models did indeed rely heavily on syntax, typically through a combination of syntactic features on the input, and then syntactic constraints during inference. So more recently, there's been a trend where end-to-end deep neural networks which use no syntax are surpassing their linguistically informed counterparts. And this is not just a trend for semantic role labeling, but this is across many tasks in natural language processing. And these models have indeed improved substantially over the models that use syntax, getting up to 23% error reduction. But the trends I've just described are mainly when evaluating on text from the same domain as the model was trained on. Out of domain, the improvements have been less impressive. So in this setting, deep neural network models have so far reduced the error rate by only 8%. And while there have been some previous attempts to inject syntax into neural models, the results on out-of-domain evaluation have been mixed. So in this part of my talk, I'm going to show that syntax really can help in the midst of deep learning with the right modeling. So our LISA model obtains an additional 10% reduction in error over the best neural network model when evaluating out-of-domain. And it also improves in-domain SRL by an additional 6%. Okay, so now I want to overview the key components of the LISA model. So the first component is multitask learning across the 4 related tasks that I just described. So in NLP, the most common approach to obtaining these annotations is to run a pipeline of models in serial, one for each task, where the output of earlier and simpler models, like part of speech tagging, are provided as input to the subsequent models, like syntactic parsing or semantic role labeling. So instead, our model is more statistically and computationally efficient by sharing model parameters across all of the tasks. And this technique of training the same set of parameters to predict multiple tasks is called multitask learning. By supplying supervision from multiple tasks to a single model, rather than providing predictions from one model as input to the next, can help to disambiguate challenging examples and reduce cascading errors. So an additional benefit of multitask modeling is that we only have to pass this sentence through the neural network one time in order to predict all these labels, rather than having to run 4 separate models and perform a lot of redundant computation. So another major contribution of this work is the innovation of integrating supervision into the neural attention mechanism. So where we train the model such that one task informs the attention patterns for the other tasks. And we do this because we want to train a more robust model by encouraging higher level tasks like semantic role labeling to rely on lower level linguistic structure like syntax, rather than on the brittle surface forms of the words. So we expect a model based on syntax will be more robust than one based on just words, because while words will change dramatically across domains, so think about going from a news article to a materials science journal article, the underlying syntax is going to remain largely the same. And I'll show that this modeling does lead to more robust performance with better generalization out of domain. All right, so now I'm going to describe how these attention models work in more technical detail. But first I want to describe at a little bit higher level how we transform text, which is fundamentally discrete information, into the real valued vectors that neural network models expect as input. Okay, so we need vector representations of words to provide to the neural network to do reasoning over. One common way that we can do this is by assigning a vector to each word and embedding the vectors of all the words that we know into a shared space where the distance between vectors in this space is a function of the word's meaning. And there's been a lot of work on how to actually approximate how close 2 words are in meaning. But the most common way to approximate this is by making the assumption that words that occur in similar contexts have similar meaning. So for example, acoustics and optics in this space would be much closer than solid state is to awarded. And this results in vectors that have really desirable properties. So for example, verbs tend to get clustered together, as do nouns. And the difference between verbs in present and past tense tend to be the same across all the verbs. And then words like these disciplines of physics will be closer to each other than they are to other scientific disciplines, and which will also be closer to each other than to other nouns like committee. Okay. So now to describe how we model words as vector inputs to a neural network, I'm going to describe how multi-head self-attention works, since we modify the internals of that network architecture in order to incorporate syntax.
So question. So,
yeah, no problem.
Something I didn't understand is, so now you have a notion of closeness, but that doesn't mean that you're able to embed it into a vector space, right? So that step is not quite, seems as clear to me. Could you explain how you did that, or did you do that?
Yeah, I mean, so basically the way that it works is we just assume that all the words in our vocabulary of, say, like a few 100,000 words, each has, 100 dimensions. You just sort of decide the number of dimensions. And then given that, we train a model based on, like basically using a large corpus of text and looking at how words co-occur with other words in the text. Does that answer your question?
Yeah, but we'll take it up later. So
Okay. And the closeness is like dot product, but yeah. Okay, so yes. Okay, so for those who are familiar, this is exactly the encoder portion of the transformer model that was introduced at NIPS last year, which is also the basis for the highly successful BERT model, which was released a few months ago. Okay, so the way that self-attention works is given a sentence and our token embeddings. The version of self-attention that we're going to use works by first projecting each token into 3 distinct representations, corresponding to each token's role as a key, query, or value in the self-attention. And when I say projection, all I mean is that we're performing a linear transformation of the input vector, which is a matrix multiply followed by the addition of a bias, where the matrix and bias are just learned parameters of our model. So each of these little arrows represents one of those linear transforms, and these are shared across all the words, but they're distinct across Q, K, and V. All right, so for each token, its query representation is compared with the key representation of every other token using a dot product. And this provides for each token a score with respect to every other token in the sentence. And these scores are normalized so that each token scores sum to 1. And these are our attention weights between each token and every other token in the sentence. So these weights represent the importance of every other token with respect to a given token. So for each token, these attention weights are then used to perform a unique weighted sum, weighted average, over the value representations for all the tokens. And so this gives a new attended representation for each token, where this new representation has now been able to observe all the other tokens in the sentence, weighted by their importance to a given token. So this is the basic self-attention model. Okay. An important aspect of the transformer model specifically is multi-head self-attention. And all this means is that at each layer in the network, we actually have H distinct sets of self-attention parameters, and they're normalized separately, and then learning H distinct self-attention functions. So this has the benefit of giving the model the flexibility to learn these H different sets of key and query values, which gives us a more expressive model, since we're doing this averaging. Okay. So these H outputs of each attention head for each token are concatenated into a single combined representation. And that concatenated representation is passed through a feed-forward layer. And finally, this representation is added to the initial input of the layer. And this is called a residual connection. So if that was layer P, this now gives us the representation at layer P plus 1, which is then input to the next layer. All right. So we typically stack J of these self-attention layers with the output of each layer provided as input to the next. And this allows the model to build up increasingly complex representations of the text with each additional layer. So now that I've described how basic multi-head self-attention works, I want to describe how we modify this to incorporate syntactic information. So returning to our depiction of multi-head self-attention, typically, each attention head is left on its own to learn which other tokens are most informative. So instead, what we do is we train one attention head to attend to syntactic parents. And we do this by replacing the query and key mechanism in that attention head by a neural network syntactic parser. So for those who are familiar with this area, it's the bi-affine parser of Dozat and Manning. So this parser produces a matrix of scores between each pair of tokens, where each score represents the probability that that pair of tokens has a directed edge in the syntax tree for the sentence. And so we can take this matrix and replace the attention matrix that was normally generated by the query key pairs. So otherwise, this layer acts just like any other self-attention layer, and we just choose one layer in the network as the syntactically informed layer. Okay.
So, question. Would you train that layer separately, or just have the architecture and let the whole thing be trained?
Yeah, the whole thing is trained end-to-end, basically through multitask learning. So we have the parsing objective in addition to the SRL and other objectives, which I'm actually about to describe. So now that I've described how we incorporate syntax into the attention mechanism, I want to describe the other important aspect of LISA, which is how we do all these tasks with just a single pass through the network. So here's the network I've described so far. At an early layer, the network predicts part of speech and predicates. And since the two labels are highly related because predicates are very often verbs, and in order to reduce the complexity of training the model, we predict into the joint cross-product space of part of speech and binary predicate labels. So at the syntactically informed layer, we share the parameters of the syntactic parser to also predict labels on the edges in the parse tree. And so now I'm going to demonstrate how we do semantic role labeling with respect to each predicate. And so while almost all previous work treats each sentence predicate pair as a separate example, where the input to the network is modified to indicate which word is the predicate of interest, our model jointly predicts predicates and semantic roles, so we can't provide this indicator to the network. Our technique is faster by avoiding redundant computation, but also requires some special modeling, which is what I'm going to describe now. Okay, so first we project each final layer token representation into an argument-specific representation of that token. And for each token that was predicted as a predicate, we project that token to a predicate-specific representation. And we then use a bilinear operator, which is just a matrix that scores compatibility between two vectors, to score the compatibility between each token with each of the predicates. So here I'm scoring Nobel with the predicate awards. And what we actually want to score for each token is what its specific label is with respect to that predicate. So we actually have a bilinear matrix corresponding to each SRL label. And so this gives us SRL label predictions with respect to that predicate. And in the same way, we score each token with the first predicate to get a complete labeling of the sequence with respect to that predicate. And we do the same for each predicted predicate. And this gives us a semantic rule labeling of the sentence with respect to each predicted predicate. And in practice, this is really fast on specialized tensor processing hardware like GPUs and TPUs, because we can score all the predicates with all tokens for an entire batch of sentences using just 2 big matrix multiplies. It's also fast because we avoid the redundant computation of having to feed the entire sequence through the network for each of the different predicates. Okay, so this is the Lisa model in its entirety. Multitask learning across 4 related tasks, with the signal for syntax shared in this special way through the attention mechanism. Okay, so I'm going to very briefly highlight some of our experimental results on semantic role labeling. If you're interested in more results, there's a lot more results and experimental analysis in the paper, so I encourage you to check that out. So first, this is the performance of the previous state of the art, which is a syntax-free neural network model. And so this is the performance of our Lisa model, except with no syntax, with syntax completely omitted. So as you can see, the performance of our model in this case is about on par with the baseline, both in and out of domain. So by incorporating syntax, our full Lisa model obtains an additional 6% error reduction over our syntax-free model in domain, and more than 8% error reduction out of domain. And so this gives us overall error reduction of 9% over the previous state-of-the-art out of domain. And so here we see that our technique of incorporating the parse is providing information that the model can use to generalize better in the out-of-domain evaluation. And having this explicit representation of the syntax does help over a very strong end-to-end neural network model. OK, so that's Lisa. It's a single model that provides 4 layers of linguistic analysis where the transfer between tasks is done through the attention mechanism. We showed that incorporating linguistic structure into a deep neural network model led to a more robust model that performed better out of domain than previous models that rely on words alone. So we've observed in practice that this model is more efficient than alternatives, and in ongoing work, I plan to more precisely quantify the speed benefits of multitask models over pipeline models in NLP. And so far we've demonstrated that this attention supervision works well for SRL, but I actually think that this style of multitask learning for generalization could have broad applications in other tasks in NLP, and even in other areas like computer vision. So stepping back, Lisa is just my most recent work focused on designing machine learning models for NLP that generalize well. So I've also done related research converting spoken language queries to actionable semantic representations, and also generalizing automatic knowledge-based construction from English to lower resource languages. So I'm interested in developing robust models that generalize well to new data. But as I said in the beginning of my talk, in order for NLP models to be of use to practitioners, we also need models that are efficient enough to scale to millions or billions of documents without sacrificing accuracy. And this isn't merely a matter of profiling and code level optimizations. Usually the machine learning frameworks that we're using have done that already for us. To get substantial improvements in computational efficiency requires developing new models and training procedures where model parameters are optimized in the learning sense for efficiency. And these modeling decisions are often tightly coupled with the capabilities of the hardware that we plan to use. So for example, the fastest algorithms on CPU are often not the fastest algorithms on GPU and vice versa. So I've also worked on this problem of developing machine learning methods facilitating fast NLP. So for CPU hardware, I developed paired inference and learning algorithms for making linear models, which are the fastest NLP models on CPU, 5 to 10 times faster during inference with little loss in accuracy. And this work earned an outstanding paper award at ACL 2015. And I've also developed an alternative model to recurrent neural networks, or RNNs, which are the basis of many slower but state-of-the-art NLP models. So by better leveraging the massive parallelism provided by GPUs, our model performs inference 14 to 20 times faster than RNNs. So this work was inspired by the success of convolutional neural networks in computer vision. But we found that we couldn't just directly apply convolutional models from computer vision to tasks in NLP. So now I'm going to briefly describe what we did to make that work. Before I do that, I want to quickly introduce another common NLP task, because this is the main task that we use to evaluate this model, and it's exemplary of the types of tasks that this model can make more efficient. So the task of named entity recognition, or NER, identifies spans of text corresponding to named entities and labels them with types like person, location, or organization. So in this sentence, we would label Nobel Committee as one named entity with the type organization, and Strickland as the other named entity with the type person. And so this task is really useful for identifying the entities participating in a document, which is the basis for a lot of NLP applications. We usually model this as a token labeling task, similar to part of speech tagging, where we perform classification for each token to determine its label. And this is what those labels actually look like. Okay. So now I've defined some desired labels, and we have the same word embeddings as before, as the input representation for a sentence. Excuse me. And so, as I mentioned before, convolutional neural nets, or CNNs, are really fast to run on GPU. And they've had great success in computer vision. But they haven't had much popularity for token labeling tasks in NLP. So in order to see why, I'm going to describe how they can be used in NLP. And then I'm going to describe how we developed a CNN-based architecture that does work in this setting. So CNNs work by encoding a token along with a fixed width window at each layer. So here I'm depicting a width of 3. So at the first layer, the representation for the token committee observes its 2 neighbors. To incorporate wider context, we simply stack these layers, feeding the output of one layer as input to the next. So at the second layer, this token observes a wider context. And we continue this to provide the outputs of the final layer. We continue this, and then we provide the outputs of the final layer to a linear feed-forward network, which performs a classification. Okay, so now we can encode each layer in parallel, unlike RNN models, which have a linear dependence on the length of the sequence. And this is exactly what makes CNNs fast on GPUs, which accelerate deep learning mainly to very high capacity for parallel computation. And an architecture like this was used for SRL in a classic neural nets for NLP paper, but it performed pretty poorly. And people seldom use CNNs as token encoders rather than recurrent neural networks. And this is because they don't incorporate enough context. So for example, compared to an RNN, which will observe the entire sequence regardless of its length, to build up a given token representation, with 4 layers in the CNN model, each token has observed only its 2 neighbors on either side. And this is kind of a short sentence, but you can imagine if the sentence was longer, this would be more problematic. So with this model, the context window grows only linearly with the number of layers. So to enjoy the speed benefits of CNNs with much better capacity for encoding wide context, I instead proposed iterated dilated convolutions. So we replaced convolutional layers with dilated convolutions, which first achieved success in computer vision, and which I'll explain in more detail in the next couple slides. So stacking dilated convolutions grows the context window exponentially rather than linearly in the number of model parameters and the number of layers. But we found that we couldn't directly transfer dilated convolutions to sequence labeling problems in NLP, where we simply have much less data than in computer vision. So we introduced a scheme for sharing parameters to reduce overfitting. We iteratively apply the same stack of dilated convolutions to obtain wider context without adding more model parameters. And we also train the model to make more efficient use of the context that's added at each iteration. And we do this by, rather than training the model to predict just at the end, each iterate is trained to predict token labels, encouraging the later iterations to use the additional context to disambiguate and correct mistakes. Okay, so first I'm going to describe how dilated CNNs incorporate context that grows exponentially in the number of layers. So dilated CNN layers have an additional parameter, which I'm calling delta here. And this controls the dilation width. So in the case where delta equals 1, a dilated CNN layer is equivalent to a vanilla CNN layer. So when delta is greater than 1, the convolution skips over neighboring inputs. So rather than composing the token representation with its direct neighbors, with dilation width 2, the token instead incorporates its second nearest neighbors. So just as with the vanilla CNN, we stack dilated CNN layers, but the trick is to increase the dilation widths exponentially. And this gives us this exponential context as the number of model parameters grows just linearly. So now you can see that with the same number of layers, the same number of parameters as the vanilla CNN, we've already incorporated context from the entire sequence into every token's representation. Yes, so now the context window grows exponentially with the number of layers. And we add a dilation 1 convolution at the final layer, which adds a little more bias towards the nearest neighbors, since our end task is actually doing token labeling and not necessarily building up a more general representation of the sentence. And classification remains the same as the CNN model. Okay. So that's how dilated CNNs work. But in order to get very wide context, like we want document level context, this model still requires a lot of layers, and this tends to lead to overfitting on NLP sequence labeling data, which is very expensive to annotate, and so we don't have that much of it. So I'm now going to describe how we share parameters in this model to overcome that. So given a stack or block of dilated convolutions, we simply take its output and feed it back into the same stack of dilated CNN parameters. Then we pass those representations through all the dilated convolutions again. We ask the model to predict the labels again after the second application of the block of dilated convolutions. And we continue this iteration some fixed number of times. Oops, sorry. And only take the final predictions as the output of the model, though we do backpropagate a loss after each application of the block. So as I mentioned earlier, this is to encourage the model to incrementally update its predictions as it incorporates wider context. Okay, so again, I'm going to quickly highlight some of our experimental results, though there's far more stuff in the paper if you're interested. So our baseline is a bidirectional LSTM CRF, which is a variant of an RNN, which has structured inference on top. But importantly, it's the most commonly used model for token labeling, and it's the state-of-the-art model for a bunch of different tasks. So when running on sentences, our IDCNN model obtains accuracy that's comparable to the RNN baseline, while performing inference 14 times faster. And when we run our model on entire documents, which is typically not done because it's so slow, our model performs inference 8 times faster than the RNN baseline. And we also see a little accuracy boost resulting from incorporating context from the entire document, which is made more computationally feasible with our model. Okay. So that's some of the work that I've done on machine learning methods for computational efficiency.
Sorry,
yeah.
Stupid question though. If your documents have variable number of words, I didn't catch how would you scale this? Are you just going to repeat the same pattern that you've learned to basically add the number of words in the document? Is that how you do it?
I'm not sure I totally understand your question. So definitely the model is limited because we train the model with basically a fixed number of parameters. So there is a fundamental limitation on the maximum amount of context that we can incorporate, versus the LSTM, which can still incorporate arbitrary context. Though I would say that though you can, when you provide any document length to an LSTM, it's technically observing everything. There is a limitation on the distance, where it can actually sort of propagate a signal. And in the CNN, those distances are, for what you can incorporate, there's more direct connections, between the representations. So we kind of hand-wavingly argue that it's maybe a better way of representing long-distance context, but we have no actual results to support that. So.
How big of a context does your CNN architecture actually?
Yeah, that's a great question that I don't know the answer to off the top of my head. Definitely, the average document length in the corpus that we used, which is a few hundred tokens. Yeah. But you could also, for whatever application you want, you can make the model bigger to incorporate more context, or smaller if you don't need as much. So in our experiments, the document model was bigger than the sentence model. Okay, so yeah. So since the overarching goal of my research is developing NLP that actually works on real problems, I do also care about applications, and to date I've successfully applied these techniques on text in the material science and biomedical domains. And I want to continue these collaborations with researchers in engineering and natural sciences, but in the future I'm also eager to collaborate with social scientists to build NLP models for social good. So for example, one way that we could use NLP to combat bias is by using NLP to identify and rewrite biased language in documents such as job ads. So there's an often cited Hewlett-Packard internal report which found that on average, men apply for a job when they meet 60% of the qualifications, whereas women apply for a job when they meet 100% of the qualifications. And job ads that list ninja or rockstar as a qualification are surprisingly common in tech, where we also have a problem recruiting and retaining women. So this seems likely to deter many candidates who maybe don't identify as such. And there's also way more subtle versions of this. So like asking applicants to be risk takers or have already made exceptional contributions in an area. And the exceptional contributions example I was just discussing with one of my lab mates. And while I thought exceptional contributions meant getting an award or some other distinguished achievement, he interpreted it as having publications in the area. So it was a very clear distinction to me. He thought I shouldn't include it in the slides. I was like, I actually really should. Yeah, so it's easy to see why this could be a problem. And one of many angles for approaching this issue could be to use NLP to automatically identify and propose more inclusive versions of this text. So another way that I'm excited to use NLP for social good is to facilitate citizen engagement, especially in local elections, by automatically summarizing local bills and amendments, and then aligning these with the voting records of our local congresspeople. So a substantial roadblock between citizen values and policy is a lack of voter turnout in local elections. So this chart shows voter turnout in mayoral elections in 30 of the largest US cities. Denver is here. And so you see that for most cities, this is far below the average turnout for presidential elections, which is also not that high. It's 55%. This is in the United States, yeah. So I think one way that we could leverage NLP to address this is by automatically extracting critical information from the text of bills, which is actually kind of really painful to read. And so specifically doing this at the often ignored state or even more local government level. And then we can align these more accessible summaries with the voting records of state senators and representatives. So this will make it easier for voters to assess potential candidates and to just engage more with their local elections and local politics. And while there are some tools out there that exist that do this, they tend to be created manually by partisan organizations. So they're curating the data by hand. And I think that doing this automatically with NLP would allow for these summaries to scale across way more levels of government and more regions and just have a bigger impact. So another important application where I think NLP will have real impact is combating computational propaganda, which often takes the form of fake news. But fake news is really a misnomer because there's many qualities aside from factuality that suggest that an article might not be the most reliable source of information. And so indeed, social scientists have researched this, and there's a number of alternative criteria that they use when they're flagging fake news in their research. So for example, there's many subtle aspects of style, such as using very emotional language or hyperbole, or the use of logical fallacies to justify arguments. And political leaning or bias in an article is also an important factor to take into consideration when trying to detect computational propaganda. A purported news venue might also have aspects of counterfeiting a more established venue. And credibility more broadly is still an important aspect. So in addition to factuality, which is a really hard problem, we can also assess, for example, the sources that an article cites. And these last two aspects suggest that a multimodal approach actually might be the best way to move forward. So this would take into account the visual appearance of a news venue and its graph of links to other websites alongside the article text, which is of course also important. And I think this is a really promising approach moving forward. So I've just proposed some applications that I'd be interested in tackling in the future, but in order for these models to work in these application areas, we're also going to have to continue innovating methods for fast and robust NLP. And I'm excited about doing that work as well. So one direction that I'm really enthusiastic about is seeing how far we can push generalization in NLP to really challenging domains and low resource languages. So as I mentioned earlier, there's going to be a never-ending supply of text domains that practitioners are going to want to analyze. And success on the news that state-of-the-art models are currently trained on is just not going to directly transfer to success for practitioners. And it's not scalable to assume that we can just annotate new data in every domain. So as an example, the data that we currently use for parsing cost almost $2 million, this is adjusted for inflation, to annotate just 2,500 documents. So this isn't going to work in the long term. So instead, what we're going to do is develop machine learning methods for cross-domain robustness. And I believe this will require developing general techniques that apply across many domains, like new techniques for adversarial learning, which allow for transfer across more complex structures than the techniques that currently exist can do. And in addition to developing domain-agnostic methods for generalization, I also want to develop techniques for leveraging auxiliary domain-specific information to provide weak supervision when it's available in new domains. So for example, in the case of materials science, we might want to link materials to rich knowledge bases containing detailed information about the physical properties of the components of the recipes. And we may even want to incorporate models of physics to help with our end task of predicting new candidate recipes. So we'll need to design models that efficiently and effectively incorporate this information for text understanding. And I actually recently submitted a grant proposal with our material science collaborators for doing just this. So I'm also excited to develop these techniques not only for robust sentence level NLP, like the tagging and parsing tasks that have been the focus of my research so far, but also for higher level natural language understanding tasks that require integrating information across sentences and documents. So for example, with the techniques I've developed so far, we can identify all the entities in a document, and then we can annotate them with semantic relations. But reasoning over entire documents allows for much more complex understanding by identifying, for example, mentions of the same entity and chaining semantic frames together. And we'd also like to integrate and extract common sense knowledge. And once we have this really rich structured representation of the document, we'll have a much better interface for interacting with the knowledge contained in the text. And so this is what I mean by whole document understanding. And once we have systems that can reliably provide these interfaces to text, we're going to need to figure out how best to integrate these interfaces to perform even higher level understanding tasks, such as question answering, which requires aggregating over many of these documents, or dialogue that's aware of longer term discourse and common sense knowledge. And anyone who has like a digital assistant knows that we're far from solving this. Okay, but so in order for these really rich models to be computationally feasible, we're going to have to keep, why is it that bright green color? Okay, sorry. I thought it was the projector I practiced on, but apparently it's all projectors, so I really apologize for that. Okay, so we're going to have to keep developing architectures and learning algorithms that are cognizant of the strengths and weaknesses of new tensor processing hardware. So a great example of this is my work on dilated CNNs, which is efficient on GPUs in particular. And the self-attention model that architecture that Lisa's based on is designed to be particularly fast on Google's new TPUs. And it's having great success thanks to this. And so moving forward, I think that we can expect to see an explosion of new hardware with the potential to further accelerate deep learning and also bring it to smaller and cheaper devices, which is really exciting. But if we simply run the same models on new hardware, we're not going to achieve that potential. We need to have more efficient machine learning having this more efficient machine learning is going to require fundamental research to develop models and training techniques that are designed with the underlying hardware in mind. And I'm really excited to collaborate with colleagues working on systems and hardware to continue to make this happen going forward. All right, so the goal of my research is to bridge the gap between state-of-the-art NLP models and practitioners with problems whose solutions can be found in text. So right now is a really exciting time to be working on NLP because a lot of our models now work really well on our sort of internal benchmarks. And so a lot of people really want to use NLP to gain insights from text. But there's still quite a bit of work to do for these models that perform well sort of in the lab to perform well in the wild. And in my work to date and moving forward, I'm excited to develop both the fundamental methodologies needed to make this happen, as well as to collaborate with practitioners to help address the complex challenges that are facing society. So before I conclude, I want to briefly thank my many collaborators who made my work possible. So in addition to having the privilege to work with great mentors, I've also had the fortune of working with an array of excellent undergraduate and more junior graduate students. And this concludes my talk. Thanks for listening, and I'm very happy to take any questions that you guys have.
The structural labels, let's take the syntax labels. Are those a pre-specified fixed vocabulary, or are those learned in the course of training? And if not, could they be, and would there be an advantage?
Yeah, so I mean, the typical supervised learning setup, or in the typical supervised learning setup, those labels are provided and they're fixed. But there's definitely a lot of work on sort of like inducing those labels. So actually in our materials science work, we have a paper in submission where we've tried to basically induce like sort of semantic labels, but in the material science domain because we don't have label data in that domain, right? So that's definitely something that people do, and that's really interesting. Yeah. Yeah.
You're seeing a lot more work with subword and character level encodings. Is like your iterated, dilated CNNs, scale or something like that?
Yeah, that's interesting. So, so it actually was a concurrent work using dilated CNNs for like language modeling, I think, and they did use a character level model for that. And I think it was successful. Yeah. So we didn't do experiments with that in our paper, but yeah, I mean, you could imagine editing it as sort of like an orthogonal thing. Yeah, that's a great question. Yeah, I think that you would get even better results basically because you have way more characters even than words, and so your sequences would be even longer. And those models work really well, but they tend to be really slow because you have to encode all these different characters. Yeah. Yeah.
So, I mean, I'm not an expert in machine learning, but the question is, your model is static, correct? Whereas in the future work, you said, you want to predict something about for example, citizen engagement or policy. But if you look at the society, it's actually dynamic. Yeah? You need to incorporate the notion of time in your model, and you need to have a memory inside your model that can capture that in order to allow you to do prediction or estimation. So have you thought about like how you incorporate the dynamic in your modeling framework or not?
That's a really interesting question. So one response to that is that I think if we develop models that are actually, really robust to new data, then like hopefully they would also be very robust as, sort of like the topics of bills or the topics of news or whatever we care about are changing over time. So they wouldn't rely on, knowing this exact word, knowing this exact person. They would have like more of a concept of, these words happen in these scenarios, this is a person, and so, yeah. But my other answer to that is, I just had a thought and now I forgot it.
But what I'm trying to say, the common sense is changing, correct? Say you talk about global warming 3 years ago had different meaning than, for example, today. So there is you can see there is this dynamic going on. So it's not a matter of robustness of your model because the whole system is actually evolving and is changing. So you need to have some sort of like memory inside your model to capture this. That's what I mean.
Yeah, I definitely agree with that, especially, I would say, I would be interested in working on that. I'd say I'm a little bit more interested in, or like maybe what's like maybe more aligned with my expertise and experience is like figuring out once you have maybe a dynamic knowledge base, like once you have some representation of common sense knowledge, how do we actually integrate that like into these models to perform better, like to be able to, do like higher level reasoning. But I definitely think that's like a really interesting problem. And yeah, there's people in my lab who actually do work on that. So, yeah, thanks. Yeah.
So it's a technical question, but like on your syntactically informed attention keyword, how do you like choose which layer to be syntactically informed?
Yeah, no, it's like. Yeah, it's a good question, and it's a common question, and essentially brute force. Like, we did a grid search, but just not over the entire space. Like, we made the assumption that we wanted like lower level tasks to occur before higher level tasks, so we enforced that part-of-speech tagging happened before syntax. But yeah, other than that, it's basically a hyperparameter, and we did find, to answer a related question that people often ask, that which layer definitely made a difference. So that matters, and that's actually something that I didn't talk about explicitly in this presentation, but that I'm really interested in working on in the future, which is like, this is like a big problem with multitask learning, is like, where do you actually put the supervision, and also how do you like trade off, like in the training objective, how do you trade off these different tasks? Because often the parameters that are best for one task are not best for the other one, and we don't really have good ways of doing that. So yeah, I'm interested in looking at that in the future as well.
Kind of related, the syntactically informed attention model was really interesting. I was wondering like how much the multitask learning versus using like the predicted like head probabilities, like how much of the did you get thrown into versus just like using standard parsers? Like,
Yeah, so I didn't go into detail on this in this presentation, although we do go into detail on this in the paper. So like one of the cool things about our model is that you can use either the parse that the model predicted, or at test time you can just like provide a parse from a different model. And actually our best results, which are the ones that I put here for the Lisa model, are from providing a parse from a separately trained model, which is why I want to tackle these problems and like how to do multitask learning better, because I think the reason that the internal model was less good is because it actually had to share these parameters, and we're like maybe not giving it quite enough help with how to best do that. I think I had one other thing I wanted to say, but I don't remember what it is. But thanks for that question. Yeah.
oh, go ahead.
No, just to follow up on that, did you try putting in the gold standard?
Oh yeah, we did. Yeah, really interesting experiments. So we, yeah, so this is great because so when you provide the gold standard, the F1 goes up sort of like across the board by a lot. So like maybe 6 to 8 points, which is actually really interesting because the accuracy of the parse that we're providing is like 96. Yeah, and so then in the paper we have, I mean, I guess I do have these slides somewhere in here. We do like a more detailed error analysis, like looking at like what mistakes, is the gold parse actually fixing? And it seems to be mostly, so one thing is like the biggest source of errors across all the models is actually the labels. So this is when it gets the span correct, but the label on the span is wrong. And I'm working on some stuff right now to maybe try to address that. But the biggest source of errors that providing the gold parse resolves is sort of like boundary errors of the spans. So if you predicted 2 spans and you merge them, that's correct, or vice versa, or kind of like being off by 1 and stuff like that. Yeah.
Let's just take maybe 1 or 2 more questions and then Strubell.
Right, so this is a very strange question to ask, but let me ask it anyway. So just convolution neural networks for vision, the way each layer is expressed is running some kind of a filter. But when you do this for text, I'm wondering if you could view parsing, like the act of building a parse tree from a sentence, given a grammar, as a sequence of convolution somehow, right? I mean, is that known? Is that well known, or justify what your CNNs are doing?
That is really interesting, and definitely, yeah, interpretability in NLP is really hard, especially compared to vision, because it's just not always clear what like a one dimension of a word embedding means versus like a pixel. It's kind of like you can just really clearly assign stuff. That's a really interesting question. I don't really have the answer to it. It's not clear to me how you could do that, but yeah, that's a cool observation. Thanks.
So I've never done this before, but I can't resist making 2 footnotes. One is on the parsing accuracy thing and the fact that the gold standard parses helped more than you expected them to. It's because the way we measure the accuracy of the parsing is crossing brackets, which is really cheating. So there's a bigger gap between that 95% and the gold standard parses than shows.
Absolutely.
And then the other one is Majid's question about, well, but what we really need to be able to do is recognize how this knowledge is changing over time. Yes, you're absolutely right, and that's the long-term goal of machine reading, is to have the computer be able to see how the language is changing in the way it's discussing these things, which is reflecting the way people's thinking is changing. But before we get to that, first we just need to do a better job of sort of understanding the plausibility of the structures that the systems are building, just you know, in a static way. And when we've done that better, then we can look at sort of recognizing how the things are changing over time. So
Thanks, Martha. Great answer.
but they were all really good questions. So let's thank our speaker again.